Today's topic is actually the exact same title as the last one we did in chemistry, and that's on purpose. We're going to talk about measurement. One of the reasons why this is so important to me is this is the heart of what science is. Okay. Science is all about, we have a problem we want to solve. We want to figure something out. Right? I want to understand why something does something, right? And what do we need to do? Well, we need to design an experiment. And in terms of designing that experiment, we collect some data and we're measuring things. Classic example I might give you would be you want to figure out whether sun causes plants to grow. Okay. Well, in doing that, you'd want to measure how much sun you've given it. So that would be like time. You may want to measure how much water you give the plant, how much fertilizer you give the plant. That could be in volume or mass. But ultimately, at the end of the day, what you'd care most about is like how much the plant grows. That might be like a distance. Does that make sense? And all of those, time, mass, volume, distance, those are measurement units. And we focus a lot on that in physics. In chemistry, we did this a little bit right at the end of the unit, where we talked about just measuring things. And really, the only units in chemistry we used were grams or moles or maybe like individual molecules. But in physics, we're going to have a lot of different measuring values, so to speak. So that's what I want to focus on today. Because remember, physics is the study of how energy and matter relate to each other. And so we need, and this word is always wrong. I don't know why I can't get it right in my notes. We need to make quantitative observations. Because what's a quantitative observation? Exactly, it has a number, right? So I don't know why I never fix my notes. Probably been like that for 7 years. But we need quantitative observations. So that's today's goal. We're not really going to do any math yet. We're just going to do some like leading in. Next week, we're going to start doing some pretty major calculations. So bring along a calculator, because you're going to want a calculator. Hopefully you even have one today. We're not doing a lot today with a calculator. Your phone will work, but like your phone won't work probably as well as like an actual calculator. So, okay, the last thing I want to point out on this slide here is that we're going to be focusing a lot on units. Many of you, when you hand it in your lab, you can resubmit it back to me because maybe the only thing you forgot to do is put a unit behind numbers. That's easy to fix. Put, if you wrote down 73.1, I might have just pointed out, guys, you just need to have grams afterwards. Okay, easy fix. Okay, but to me, that's really critical in physics because it could be a meter. It could be a kilogram. It could be a Kelvin, which is temperature. It could be a second, right? And so we need to make sure we do write down what type of unit we're referring to. Okay. What I want to make sure that you guys are fluent with and familiar with then is this staircase concept of like prefixes. In theory, you learned this in like middle school or junior high math class at some point. In theory, but like I need to give you a review because in case like I don't know, maybe you didn't really pay attention back in grade 7 math or whenever you learned this. I need to make sure you get this concept. So the idea is that we have these letters that go in front of things, like say kg, that is a kilogram, or km, that's a kilometer. You guys have heard of these before? Okay. And then you've got things like cm for centimeter or mm for millimeter. And you can really do this in front of any unit. So if I were to go back to the units that we had on this page here, for example, even though we're never going to use an amp in this course, I mean, if I gave you an amp, hopefully you would know that a kiloamp is bigger. And if I told you that you had a milliamp, that's like a very small part of that. So here's what I found works best. You probably learned the staircase thing at some point in your life in a math class, or maybe you don't remember, maybe you never did, I don't know. I like this table here, okay? And if you guys would like, you can cut this out of your notes and tape it onto your data sheets if you'd like, because I think this is the single best table I found for showing kids how to use this. So if you'd like to later, literally like cut it and paste it if you want to. Okay. Here's how the table works. You actually have to draw like a little line right about here in the middle. It's between the deca and deci. And this would be like your standard unit. That's where that would go. Your standard unit. Okay. As an example, today, I'm going to use the unit byte. B-Y-T-E. What do bytes measure? Data, storage capacity, right? And if you guys have a cell phone with like a 2 gigabyte plan or a 10 gigabyte data plan or whatever your parents pay for or you pay for, I'm going to use that as an example because I think that one most kids understand. Okay. A byte is like a small unit of data, but most people, like 1 byte would not be enough. So probably the first unit you guys would know of would be like, say, a kilobyte. Like a Word document might be a couple of kilobytes, right? Well, that is 1,000 of them. And you can see that right here, there's 1,000. So if I had 1,000 bytes, that would actually be 1 kilobyte. Does that make sense? This 1,000 tells you how many of them you have. But like bigger than a kilobyte is a megabyte, which is 1,000,000. Or bigger than a megabyte is a gigabyte, which is probably what you guys are most familiar with. A gigabyte is 1,000,000,000 of them. A terabyte, I have a couple of terabyte hard drives. Those are quite large. That's the next unit up. That's 1,000,000,000,000 of them. Did I have that right? Yeah, that's, what is that? Hundreds, thousands, millions, billions. Yeah, a terabyte is 1,000,000,000,000 of something. And then, I mean, I don't know if they even have these things that go that big, but if you want to, you can get up to peta, exa, zeta, and yottabytes. Now, the same thing, though, applies to whatever unit you have. So if it wasn't a byte you were talking about, but let's say it was a meter. Let's say it was a meter. If you have 1,000 meters, you call it a kilometer. That makes sense? So everything on the upside of the table, these are very large values. You use them when you have a big number. Does that make sense? When you have a lot of them. And all you need to do is know how big it is. And so they're actually in like multiples of 3 usually. It goes like 3, 6, 9, 12, 15, 18, in terms of how big they are. On the opposite side of that, if you go down this way, these things are things that are very small. And you're probably familiar with a few of them. For example, a centimeter. A meter, if I were to like measure it out on the board, maybe a meter would be like from about here to here. I don't know. If I went up to the board, maybe that physically would be how far a meter is. I don't know. Maybe I'm estimating too small. Well, a centimeter would be like from there to there. Does that make sense? Right? Like a centimeter, if you guys can see my fingers, right? A centimeter is about this big, right? And a meter stick is about that big, right? And so anything that's in the smaller section here, you have a fraction of. And the way this table has done it is it's gone like 0.1 or 0.01. I like actually using this, 10 to the minus 2 if you can't see that. What 10 to the minus 2 really means is that you're dividing by 100. And 10 to the minus 3 means you're dividing by 1,000. And 10 to the minus 6 means you're dividing by 1,000,000. Right? These ones up here, you have to have 1,000,000 of them to have one of them. So if you have 1,000,000 bytes, you have a megabyte. But if you have 1,000,000th of a byte or a meter or whatever it is, if you have a very, very small fraction of it, then that would actually be like a micro or a nano something. We measure some things in femtometers, which is like the tiniest fraction of a meter. Does that make sense? So what I want to do on the next couple slides then is help you guys be able to convert fluently between these different prefixes for any unit, whether or not we're using it yet or not. So let's try some examples. Hopefully this will help. The question you have to ask yourself every single time is, do we need to make it bigger, or smaller? That's the question you have to ask. If you need to make a number bigger or smaller, depends on whether you need to multiply or divide. That make sense? So here's the question. And maybe this is going to seem backwards at first, but if I'm going to go to kilograms to grams, should this number become bigger or smaller? The answer is bigger, because there are a lot of parts in a kilogram, and if you're going to go from a kilogram to a gram, you better have like a lot of those little grams in there, right? Okay. So we need to make this number bigger. Okay. The basic idea, I think, would be that if you are going from, like, say, a kilo something back to the standard unit, you're going to need to multiply. If you're going from somebody up here back down that way, you're going to need to multiply and make it bigger. So how big is a kilo? A kilo is 1,000 of something. So if you have 8,000 kilograms and there are 1,000 grams in a kilogram, you just need to times this number by 1,000, which means the answer is 8,000,000 grams. What I've done is I've just added 3 more zeros. Let me try a couple examples with you, and maybe some of you are going to look at this and go, yeah, Chris, I got this, which is 5 to 10 minutes here, but this is really critical in physics, is not knowing how to use your prefixes. So let's try another one. I'll use a new color here. When you're going from a meter to a centimeter, the question you got to ask yourself is, should you get more or less? If you're going from a meter to a centimeter, you need more. Why? Well, because centimeters are very small, right? And so if you're going to have those centimeters, there's 100 centimeters in a meter, right? So for every meter, you need 100 centimeters. So this one right here means you need to times by 100. So for this one right here, you need to make it 589 meters. And if you're really struggling with where I came with the 100 from, go back to this chart right here. You'll see that centimeters had 10 to the minus 2, which is like two sets of 10. Only this 2 sets of 10 is 10 smaller, which means you need more of them though, right? Let's try this one here. This one's backwards now. We're going to go from seconds to ms. So right off the bat, you might not even know what the capital M is, so let's go to the chart here. Where is capital M located? Mega. It's right. I'm just going to delete some of this stuff. It's a mega. Kind of like a megabyte. You ever heard of that before? So I'm just going to erase all this so it's not so cluttered anymore. This is mega. Here's the thing we need to know. A mega is a 10 to the 6. It's a million of them. So the question we have to ask then is, if we're going from seconds into megaseconds, do we want this value to become bigger or smaller? This time it's smaller, because if you have a million of them, then you have like a megasecond. And so if we're going the other way, if you're going like down, you're usually multiplying by something. But if you're going uphill, you're usually dividing. That's kind of a good rule of thumb. I'm going to go from the base unit that was right here up to mega, and so I'm going to need to divide by 10 to the 6. So back on my notes here, I need to take 98000, and I need to divide by 10 to the 6, which is a million. Now you can use your calculator if you want, or you can just move the decimal place over 6 times. So the decimal place would be like here at the end of the number, so move it over 1, 2, 3, 4, 5, 6, and if this makes sense, it's going to be 0.098, I guess we'll call it. That is how many megaseconds you have. And if you wanted to check your work, if you were to take this number and times it by 10 to the 6, you should go back to this again. Because really, here's how this works. If you have 0.098 megaseconds, just take the capital M, replace it with the 10 to the 6 that was there, and if you were to times this by that, it would actually take you right back to the number you had right there. So that's actually one way you can think of things, is that if you have a prefix in front of something, replace that prefix with the times 10 to whatever power it was. Let's try another one. Here we have 0.065 kilomoles. I'm going to even ignore what I'm turning it into for right now. I'm just going to talk about what a kilomole is. As soon as I see this K right here, if you'd like to, you can just replace it with whatever prefix there is. So what is a K? A kilo. A kilo is 1,000 of something. So I could say that this is really 0.065 times 10 to the 3 moles. And all I've done is I've replaced this K with times 10 to the 3, because like I said on this chart here, what is a kilo? A kilo is a... And so if this makes sense to you, then, so I'm going to have to go down below here, but then just times this by 1,000. So 1, 2, 3. This is actually 65 moles. Okay, but I actually want to convert it into d moles, whatever that is. So let's go find out what a d mole is. And it's right here. It's deci. And so you know what I was actually doing is I was going from kilo back to the base unit, and in going down, I times by 1,000, right? Going down the chart means times by 1,000. But I actually have to go from here down one more. So you know what I need to do is I need to times by 10 more, yeah. So I really just need to times this by 10 more and make it 650 d moles. Then if you wanted to check your work, just in case you're like, oh, I'm not sure I did it properly, what does the d stand for again? You could have replaced the d, it is deci, but d was also times 10 to the minus 1. Well, if you took 10 to the minus 1, that just means pull the decimal place backwards 1. Wouldn't that get you to 65? Which is kind of our halfway point. So if this makes sense to you, I feel like kids are going to fall into one of two camps. Either they're like, yeah, Chris, I got it. I know how to convert between kilos and centis. That's fantastic. If this is something where you're like, ooh, I need some practice, I'm going to do one more example on here, and then I have a slide here that you can try on your own later if you want. Does that make sense? And I'll come check it if you want, but I feel like usually that's where kids fall. Either they're like, Chris, I'm bored. Can we move on? Or I'm not even getting it still, and I need to talk with you more later. Fair enough? So I'll do one last example, then we'll move on. Let's say I wanted you to convert 87.7 amps into a GA. Okay, first question, what is a GA? It's a giga, right? So go to your chart, figure out what capital G is. Giga. What's the like number for giga? A giga is a 10 to the 9. Okay. So what we could do is we could say that we had 87.7 amps. And if I wrote it with a giga, though, it's not 87.7 times 10 to the 9, because like we're trying to go the other way. I want to know how many gigaamps do you have if you have 87 amps, and like you need 1 billion of them. You need 1 billion of these to have 1 gigaamp. Do we have 1 billion? Not even close. We should have a small percentage of this. So it's not times by 10 to the 9. If you're going up, you might notice I wrote it on here, right? If you're going from the base unit right here up to giga, you need to divide. So we need to take this number right here. I'll just put it way up above here now. 87.7, and I need to divide by 10 to the 9, which means I need to move the decimal place over 9 times. So it'll be 0. I'm just going to try to count it out. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think this is my number. Just going to count it out. So the decimal place used to be between this 7 and this 7 right here. So it should have been moved over 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So this is how many gigaamps do you have. Do you have a lot of a gigaamp? Not even close. Measuring this in gigaamps would be a really poor choice. And to just reconfirm your work if you really wanted to, if I wanted to double check, I could rewrite this number, and instead of writing giga right here, I could write it with times 10 to the 9. That's an A hidden back there. This 10 to the 9 is like the replacement for giga, and if I times it by 10 to the 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, yeah, then it's 87 again. Okay. So long story short, you're either multiplying or dividing. By something. 1 million, 1 billion, 1,000, I don't know what the number will be, right? You've just got to figure out whether to make the number bigger or smaller, okay? If this makes sense to you, fantastic, we're moving on. If this doesn't make sense to you, can I chat with you more later? Okay. Sometimes I think teaching's like, the analogy I hear is like bowling. You know, when you bowl your first pin down the lane, you're trying to knock over as many pins as you can. That's what I'm doing right now. And if you got this, fantastic. But like sometimes you miss a few pins. So like if I've missed you right now, I'm not quitting. Okay, but can you come talk to me later and I'll try to help you explain it more like one-on-one or in a small group? Sound good? Okay, try this slide later if you want. Let's move on. Let's review scientific notation then. There are some numbers then that are so large or so small that we really need a way to like abbreviate them. I'll give you a couple of really common physics examples. This is how far it is to the sun. That is a lot of meters. Okay. And writing that number out every single time is honestly a little ridiculous. And so what we sometimes like to do is write it in this notation, something point something times 10 to the something. And I showed you guys this already. For example, this top number here, maybe it would be best to write it as 1.49 times 10 to the, and then you can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Maybe I'll write it like this instead, that many meters. That's a kind of a shorter way of writing it. I could write it like this, by the way. I could, rather than moving the decimal place over 11 times, write it as 149, and then move it over 1, 2, 3, 4, 5, 6, 7, 8, 9. But then rather than saying 149 times 10 to the 9, I could call it 104 meters. That's also possible. So sometimes we want to find a way to shorten up these numbers because they're too long. This number right here, I can move the decimal place over, like say 1, 2, 3, 4, 5, 6, 7, 8 times. I could call this number 2.0 e negative 8. That's another shortened way we can write things. So hopefully you remember me showing you a little bit about this when we did our mole for the first time, because this is not brand new. But I just need to review that we're going to have numbers that are big and small. We need a shortcut for writing them. Here's a couple of example slides. Let's just do a couple of them. I won't do them all. This first one right here, you can move the decimal place over 1, 2, 3, 4, 5, 6 times. You could call it 2.6 times 10 to the minus 6 seconds. Or, why don't you just call it 2.6 microseconds? Because a 10 to the minus 6, if you go back to that chart there, is this little funny looking U. It's called a microsecond. You can do that. Both would be valid. Or this one right here. I could call this 1, 2, 3, 4, 5, 6, 7, 8. I could call it 2.6 times 10 to the 8 meters. That's fine. Nothing wrong with that. I could even do this, though. I could go 1, 2, 3, 4, 5, 6. I could stop right here and call it 260 times 10 to the 6 meters. And then since a 10 to the 6 is a mega, I could just call it 260 megameters. Either of those works. But what we don't want to do is keep writing out these stupid long numbers or stupid small numbers. Like that's not reasonable. Now this last one right here kind of leads me into the next topic. You know how like I had all these zeros afterwards, and by shortening it up, I didn't have to write all the zeros anymore? Sometimes though, you're going to get a number like this, and we need to round it. There were some rules we learned for rounding that I want to revisit as well. They were called significant digits. Because if I were to write this one out, maybe I could write it as 8.0170797 E8 grams, because I'm going to move it over 1, 2, 3, 4, 5, 6, 7, 8. But like, if I write out all of the digits, does that actually help? I mean, wasn't the whole point of this to like shorten it up a little bit? Okay. So that leads me into our next discussion of rounding. And I'm going to start, though, before I get to rounding, of reminding you about precision and accuracy. It is really one of the most important concepts I need you guys to know, just as scientists. I know maybe you're not all planning on being scientists, but like the vocabulary is important. Accuracy is like whether or not you're right. And precision is like how zoomed in you can be, or like how exact you could be. Okay? I did this little game, if you guys remember the other day there, where I asked you to find the Eiffel Tower, right? And if you could like zoom in on your screen, like really, 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 really zoomed in, that's precise. And that would be the example between these two different rulers. This ruler here is more precise because like there's like more incremental line markings on it, right? It gives me more information. Accuracy is whether I measured it properly though. Okay. So like let's say the object was actually this far, but let's say that like I just suck at using a ruler and like the back end of the object was right here. Right? Well, then I'm not using the ruler properly. Okay, that's accuracy if you're doing it wrong. Okay. These are some more picture slides discussing the same concept. Let's get to our SIGDIGs then. The rules for SIGDIGs are if you 48, that has 2 digits. 48.2, that's better. That's more precise. 48.21437, that's even more precise. Yeah, don't even ask. Put your name on the board. So the more digits you can provide, the more precise it is. So the basic rule is any digits that go this way here, they count as what we call significant digits. They matter to us. But any digits that are on this side of your numbers, they don't count. Because I could keep writing zeros for forever on the other side there. Because really, what does this mean? It means I have 8 ones, 4 tens, 0 hundreds, 0 thousands, 0 10,000s, right? We would never like write zeros on this side here, right? We don't bother with them. Okay. Yeah, I've already kind of given you guys these rules, so let's just do a quick review with these numbers here. If we measured these, how many digits would they have? So I'm going to go fairly quickly through this. This has 1, 2, 3 digits. Right? This one right here, though, only has 2 digits. And the reason why is that this 3 counts right here, this 4 counts right here, but this 0 right here, it's kind of iffy as to whether it could count. Let me give you an example as to why. Let's say that it was actually 339. Maybe it was rounded to the nearest tens, and when you round it to the nearest tens, it would round to 340. That makes sense? But maybe it was actually, maybe the number was 336. Wouldn't that also round to 340? Right? And so if we were rounding to the nearest tens, maybe that's what it turned into there. So this 0 right here is often very tricky. Some people say we should count it. Some people say we shouldn't. Maybe it was actually the number 340.2. And what we did is we rounded off the decimal place. So this one right here, some people think it's 2 or 3, depending on whether you're rounding to the nearest ones or the nearest tens. So because of that, we really don't like to write numbers like this if we can avoid it. It would be better to write it as 3.4 E2 or 3.40 E2. Because now I know for sure whether or not I measured that last place or not. Now I know how zoomed in the measurement was. So this one right here is a little bit of like an iffy one as to whether or not we should count that 0 on the end. Let me try explaining that one more time here. Let me give you a number. Let's say the number was 339.4142. Let's say that was a number, and I told you I want you to round it. So let's say I said you to start rounding. You cut off this number, you cut off this number. Actually, I'm going to change what I had there again. Sorry. Let's go with 336.7135. There, I'll use that. Let's say we started to round. So I said round off this number, and then you got to here, and I said I want you to round this to the nearest one, like to the nearest ones. This 7 means you would round this number, and it would turn into 337. But what if I said don't round to the nearest ones? What if I said round to the nearest like tens of something? Okay. If I asked you to round 336 to the nearest tens, that would round it to 340, right? Because like you'd either get 330 or 340 or 350 or 360. Okay. And so depending on whether this was rounded to the tens or the ones, I'm not really sure how precise this number was. So we really try to avoid writing them like this because it makes it a little bit ambiguous. Let's try some more typical examples though. How many digits does this guy here have? 2. Because these zeros right here, those are just placeholders. What about this one up here? 1, 2, 3, 4, 5, 6 digits. This guy right here, 1, 2, 3 digits. Okay, I've skipped over a couple on purpose. You might be wondering, Chris, why did you skip 12 eggs? 12 eggs is a bit of an anomaly. It doesn't have sig digs. Here's why. Can you have a part of an egg? There are certain things in measurement where you can only really have them in whole numbers. For example, if I measured how many kids were in this classroom, there's no way that I should measure 33.97 of a kid, right? Because like you can't have whole numbers. So I wanted to point out that there are a few times in science where if I asked you to do significant digits, it's not applicable. Because like I can't have a portion of an egg, right? This number, there's no way that this number was 12.35 eggs, and I rounded it to 12. Because you can't have 0.35 of an egg. You either have 1 or 2 or 3. Okay, this number down here then. This number is very, very precise. There's actually a whole lot of digits to it. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think there's 13 different digits there. So this is actually a very, very precise number. Lots of value to it. This one right here has 5. This 0 here does not count. It's a placeholder. But any zeros that go that direction, especially after a decimal place, mean that like we took the time to measure it even more and more exactly. So this guy would have 5 digits. This last one here though, yeah. Did I miscount? These ones right here? Okay. So any number that's after the decimal place, if I take the time to bother writing out that it's a 0, it probably means that we actually measured that it was a 0. I want to illustrate that actually with this last one here, because you might say, Chris, why did these zeros, why did they count, and why are these ones kind of messed up? Let me try to explain this concept again with 300. This could be 1 or 2 or 3. Here's why. Let me give you some possible numbers that rounded to this. Let's say that the number that we originally had was 300.124. And I asked you to round it to the nearest ones column. So like you got rid of this number, you got rid of this number, and what does the one rounds down, you stopped here. That was me rounding to the nearest ones. However, this number could also have been this value here, 296.173. And I was rounding to the nearest tens. Because if I rounded to the tens, you'd get rid of this, you'd get rid of this, you'd get rid of this, and you'd want to get rid of this 6 right here. But what happens when you round a 6? A 6 rounds up, and so this number here would also round to 300. Does that make sense? Or, here's another possible number. Maybe this number was actually 251.136. And as I rounded this number, let's say I asked you to round it to the nearest 100. Well, then you'd get rid of this digit and this digit and this digit. This one right here, you'd kind of want to get rid of as well. And then like 250 is like slightly more than halfway. If I round to the nearest 100, it would also round up. And so numbers that end with zeros like this, not after the decimal place, but like numbers like this one here and this one here, they're very like confusing as to what we rounded to. It could have been rounded to the tens, the hundreds, or the ones digit. So we do, to the best of our ability, we try to never write these numbers in this format here because we're actually not sure how many sig digs they have. Did that make sense to you? Yeah. Yeah. Count those two. I chose not to. Good question. Okay. So these ones right here, if this is the ones you're referring to right here, those are numbers that are like on the opposite side there. And so, you know how like, let me try another example here. You guys ever do this when you're like in elementary math? Like my daughter's learning how to do this. There's like a place card. And like they gave you manipulatives. You ever get like those individual like blocks and they called those the ones? And they gave you like those sticks that looked like this and they called those the tens. You guys know what I'm talking about? And they give you like the square, they called those the hundreds. And they give you the cube. You guys know what I'm talking about here? And then there's a decimal point. And then you have the tenths. And then you have the hundredths. I'll just write 1 over 100, right? 1 over 10. Okay, here's what I'm trying to describe to you here, is that often when we have a value, like a number of some type, we don't have any thousands. And we don't have any hundreds. And we don't have any tens. And I might give you the number 3.5. This means that you have 3 ones and you had 5 tenths. So any number on that side right there doesn't count. But then to answer your question then, let's say I gave you a number that was like 0.00025. Well, this means you have 0 ones and you have 0 tenths and you don't have any hundreds and you don't have any thousands. Well, in the same way that like the number 0.00025, we wouldn't write those numbers normally, right? Because that's kind of ridiculous to like say the number 25 has 0 of these and 0 of these. I could keep zeros going that way for forever. So for normal numbers, we don't bother writing these. But for decimal point numbers, we have to. We have no choice. We have to write this decimal here so that we know like exactly how far the zeros go. But by that same logic then, these zeros, they really don't count as like us having any values in these placeholders. Does that make sense at all? Okay, so let me go back here again. So one and not the other. So you're talking about these zeros here. Okay. So these zeros here are on like that side of our values right here. These zeros right here though, those ones are on the opposite side of our measured values. So what this means here is that somebody zoomed in even further. Okay. These ones right here? Oh, okay. So because there's numbers between them, like here and here, like let me give you a different example then. If I were to give you the number 107, I would say this has 3 digits. Because I measured there was 100 block. There were 7 ones. I just happened to not have any 10s, but like that was a measured value. The measurement for that was 0. I just didn't happen to have any. So any numbers that are like between 2 values that happen to be a 0, they still count. It just, like there's a 1 in 10 chance it could be a 0. Does that make sense? So maybe I should go through these rules a little bit more carefully here then. Because if you just want some systematic rules, anything that's 1 and 9 always counts. Zeros between digits count. So if you have like 1007, this is 4 digits. This one, this one, this one, and this one, they all count. But if you had the number 1000, that's tricky. Because now there's not like another digit in between there. And so 1000 could have been rounded to the thousands, to the hundreds, to the tens, or to the ones. And we're really not certain about that one there. So anything to the right of a decimal point though, as soon as I start doing this, now I've taken the time to like be exact. Now we count those zeros. Anybody else have questions you may want to ask on this? Feel free to ask right now. And by the way, I really should do this in smaller groups later as well. But yeah. Yeah, this one down here. You're right. Okay, so that's a good question. So you're talking about these 2 zeros right here. Okay, so if we take the time to write out the next number, like, let me give you a different example here. How old are you? Okay. But like, you're not exactly 15. You're 15 point something, right? And so if I wanted to be more precise, if I take the time to say that you're actually 15.3, that 3 should count as like more precision, right? Well, what happens if today is your birthday? If today is your birthday, wouldn't you be like 15.00? Does that make sense? And so if I take the time to write zeros out on this side right here, it just so happened that it was the lucky day that those numbers actually were zeros. Does that make sense? But would I write the zeros on this side over here? No. So any zeros over here, they don't count. But after a decimal place, if I do put zeros here, it just so happened that was what the number would have been. Okay. Otherwise, I could just be lazy and just like when you gave me your age, you just kind of tell me it to a whole number. Does that help answer your question? Okay. So what makes it really tricky then is if you ask me how old I am and I say I'm in my 30s. Because that's a little ambiguous. I could be 30. But I could be like I am 33 and I rounded it to the tens. You get what I'm saying there? So zeros that are before a decimal place that are like right here, those are wishy-washy. So we really try to avoid those ones. Okay, let me talk more about sig digs maybe later in like smaller groups if you want. Okay. Let me do a couple more thoughts and then we're gonna have to call it quits because class, what time does class end again? Yeah, so that's pretty quick here, hey? Okay, so give me let's say 2 more slides and then we'll call it quits. The reason why these sig digs matter so much is that sometimes we are adding and subtracting them to each other. And that becomes a bit of a problem. Here's a really exaggerated example. Let's say that I asked you to add 2.2 and 18 point blah, 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 like I made it really long. One of these numbers was measured very precisely, like it was, this one right here, the bottom number, was zoomed in really, really far. These zeros right here, they just happened to be a 0 when we measured them. Does that make sense? Like there was a 1 in 10 chance that I measured it, it was a 0, right? And so we were really exact. But this number right here, this 2.2, someone rounded it way too early, which means that maybe this number was 2.21739. Like, maybe this is what the number was, and it got rounded. Okay. The problem we come across here then is that we have like an incongruency where two numbers being added together. It's not really fair to add them because one is very precise and one is not. So the rules we use are that we cut things off at the least precise location. If this guy can only be measured to the 10th, can you stop, sir? Thanks. If you measure this number here to the 10th, and this number here got measured to like the billionth, when you round your final answer, here's what the answer would be. It would be 20.4. That's where we would cut it off. Okay. And even though this guy right here had more digits afterwards that I didn't know, I don't keep the 7, 6, 7. I don't keep those numbers, though. I have to cut them off. Actually, I lied. That would be 20.4. Because I knew that there was at least a 6 here afterwards, it would actually round up. The 6 would round this up to 20.5. But that's where we'd have to stop. Grace, was that your question? Okay. I'm glad you're a little ahead of me there. So, but like, I don't get to like keep all these digits here because like this number right here, I didn't have them. So that's rules for adding. And then the last thought, rules for multiplying. You just take the least number of significant digits. It helps you round. So if you guys have a calculator nearby, can someone tell me what 3.8 times 14.6 is? Just get me that value. 3.8 times 14.6. 55 point what? 48. That's where it stopped there? Okay. Okay, so what I want to discuss here is the fact that we started with a number that had 2 digits. And we multiplied it by a number that had 3 digits. And all of a sudden we have an answer now that has 4 digits. And not only that, these digits were to the nearest 10th, and now it's going to the nearest 100th. When you multiply and divide numbers, you often get values that have like way more digits than you started with. It's kind of not fair to keep all those digits, we have to round. So the rule is, whoever had the least number of significant digits, that's what we round to. So since this guy only had 2 digits, this guy here, when I'm done, should only have 2 digits. So round this guy off entirely, and then since 4 rounds down, this number would have been 55. Okay, why don't we call her quits there? I think this is a good ending spot as any. If you guys would like, maybe now ask me some questions in smaller groups, because if I wasn't able to like fully explain it with the big group, maybe I can do a better job with like people in 1 or 2. Okay. On Monday then, we'll finish the set of notes. I only have a little bit left. There's a couple of examples left, and then we're going to talk about some velocity. So let's try to finish this off, and we'll do another set of notes on Monday. Sound good? Okay, so find me if you do have questions.